So the next thing we're going to talk about is the number e. So in many applications, the most convenient choice for a base is an irrational number, which seems weird. It's convenient and it's irrational. But that number is the letter e. It stands for Euler's number. Euler was the guy that really, well, he didn't really discover it, but he got credit for it. So e is approximately equal to 2.718281828. There's a lot of eights to start, but it's going to be a non-repeating never-ending decimal place. We're going to call it the natural number or the natural base. So we can use our calculator to evaluate what would happen if we did f of x equals e to the x. So for example, x to the negative 2, we'd be doing f of negative 2 equals e to the negative 2 power. Oops, sorry, not to the negative first, to the negative 2 power. Now, on your calculator, I don't have this up on my screen right now, but if you look at a graphing calculator, a TI-84 or an 83 or what have you, if you look on the right side above the division, you'll see a color. It's on my calculator, it's yellow. I think on the 84s it's often blue. But if you do second divide, that should give you the e symbol. And so we're going to do e, and then we're going to do raised to the, so we're going to use the caret symbol right above the division symbol, raised to the negative 2, and we're going to get a decimal of 0.1353, and it keeps on going forever and ever and ever. So let's just go 4 decimal places and call it good. Plugging in f of negative 1. You can plug these in on your own. In fact, I'm going to encourage you to pause the video before you go any further. And clearly you've paused it. So I'm going to say f of negative 1. We're plugging that in. E to the negative first is about 0.3679. Next one, f of 0.25. So we'll do e to the 0.25, which gives us approximately equal to 1.284. And the last one will do f of 2.25, so e to the 2.25, and that's approximately 9.4877. Oh, I forgot a 0 on that last one. So this number seems kind of nonsensical at first, but this number is going to come into handy for various compound interests, so dealing with money. So, beyond basic computations, the natural base e is used in many applications, as I just said, such as compound interest. So after 2 years, the balance A on an account with the principal P, the starting amount, and the annual interest rate of R as a decimal, so we have to take the percent, convert it into a decimal, is given by the following formulas. So if it's compounded n times per year, it would be A equals, the final amount, equals P times 1 plus R over n raised to the nt power. Now if it's continuously compounding, it'd be A equals P times e to the RT power. So we're going to go through this, a couple examples down here. We've got a total of $12,000 being invested in an annual interest rate of 9%. Find the balance after 5 years if it is compounded various ways. So we're going to do quarterly, monthly, and continuously. Which way is going to be best? So going through those numbers, this 12,000, that's our P. The 9%, that's our R, but remember, we got to convert that to a decimal. 9% as a decimal is 0.09. 5 years, that's our T. So compounded quarterly, that means 4 times a year. So we're going to use the first one. We got A equals P, our principal is 12,000 times 1 plus our rate of 0.09 over, it's compounded quarterly, so that means it's compounded 4 times per year, once per quarter, raised to the nt power. So it's 4 times our total number of years, 5. So again, quarterly, it's as if n equals 4. I kind of glossed over that. My apologies. So after we plug that into a calculator, you do not need to do that all by hand, but if you want to make it a little simpler on yourself, you can make it 12,000 times 1 plus 0.09 over 4 raised to the 20th power. Sometimes it's nice to have that as an exponent. Otherwise, yeah, don't worry about it. After you plug that into your calculator, you end up with a total of $18,726, and we should go 2 decimal places because we're talking money, 11 cents. Let's try another one. Monthly. That means n equals 12. We're compounding in 12 times in a year. So we got the same equation, just different, well, slightly different numbers. We got A equals 12,000 times 1 plus our rate is still 0.09 divided by 12, because we're compounding it 12 times per year, raised to the 12 times 5. Now let's clean up that exponent a little bit. We got A equals 12,000 times 1 plus 0.09 over 12, and then 12 times 5 is to the 60th. After you plug that into your calculator, you get A equals, your final amount is $18,000 again, $788.17. Now, for continuously, that's as if n were equal to infinity. Now, things get a little goofy if we were to actually plug an infinity there, but we're going to use the formula A equals P times E to the RT power. P times E to the RT power. So we're going to do A equals 12,000 times our E value, which we'll use on the calculator, raised to the R, so 0.09 times your time, which is 5. If you want to clean that up a little bit, that'd just be 0.45. But once you punch that into a calculator, you get $18,819.75. So compounding continuously gains the most money.